Hello, today we're going to see a very beautiful problem which has an important role in how we see today's the theory of sciences. This very notion of theory of everything, how has that evolved? So we're going to see the history of problem and we're going to solve it with using soap films. So let's see what's the problem. The problem is known as the fastest descent problem. The problem is if you drop this ball from point A and you want it to go to point B, with which curve would you slide this ball so that it reaches this point the fastest? So if I show you in this this setup, here is all these points are this point A and this is point B. So how would you make the slide so that when you slide you will reach this point fastest? So maybe we can think that it could be the straight line because that's the shortest path, but when we are taking the shortest path, it's not the fastest. Why? Suppose if you just make the other slide little bit which goes down earlier and then straight. So if I have to go from point A to point B, then maybe I can think that, oh, I go straight and that could be the fastest. That is for sure the shortest, but not the fastest. Why? Because suppose if I just go earlier more down and then at point B, then I would gain more acceleration initially only, and then this velocity will provide me some help to reach the point B fastest. But what will be this curve such that this total, neither the length increases too much nor also I get the advantage of this downward acceleration due to G. So this was a very famous problem a long time ago also. Galileo tossed this problem in 1638 and said that this curve such that it will go fastest will be a semicircular arc. So let's first try to see what it will be. So we have our setup here in which we have different slides. Which one do you think will go fastest? A, B, C, D? Please comment down below. So let's see. So we can see that this option number B wins. So it's not the straight line which is the fastest. It is somewhere other curve, but what that curve is. So this was a very interesting problem and many scientists were going through, oh, what this would be. And then some 60 years later, Bernoulli came and challenged this solution of Galileo that I don't think it's semicircle, and he proposed his solution, something that he didn't tell what his solution, but actually he challenged different scientists that, what do you think, what would be the answer and all. And then he challenged different scientists like Newton and everyone. So Newton actually also figured out, but then Bernoulli still said, I feel that my solution is something much more than a solution, and he was like very happy about his solution. So what was exactly that which actually made him so happy about his solution? It was this beauty of merging science, from where this quantum physics actually started. Bernoulli so happy about his solution is this nature of his solution. So actually what he did is not just calculating this answer by maths, but he used some trick, a very intelligent trick. What he said, if we have to go from point A to point B under this gravitational fall, he said that we know at least one thing which goes, which always take this fastest path, which is light. So we're gonna use light to answer us that what would this slide be such that when I roll my ball from A to B, it goes fastest. Now how we have to use this light is interesting. So first let's understand the scenario of how this ball is rolling. So I take any slide in any way. If there is no friction force, then I can say that what is happening is this potential energy is getting converted into the kinetic energy. So for my point to go from A to B, however is the slide, what I know is that if it goes y down, potential energy will change by mgy, it get decreased by mgy, and this change will go by half mv square to the kinetic energy. So my velocity will be proportional to root y, and this, like, if I am thinking that there is no friction and this type of force, so I know that whatever this slide is, whatever path I take, either straight line or semicircle or anything, if I come y down, then my velocity will go as a function of root y. The thing is, how should I change this curve as a function of y? That was the question. So now we have to come back. What was our question? Our question was, we have to go from point A to point B. We have to make a slide such that it goes fastest. And what we have seen, that in whatever slide it is, my velocity is going to be root y. And now what it uses, that light actually takes the fastest path. So it says, suppose I give light an environment such that its velocity increases by root y, that if it moves y in one direction, its velocity increases by root y, then whatever path my light will take will actually show me how I should make the slide. So if we think of it, what it did is, it said that I know that velocity is proportional to root y, so I have to make something like, to change the velocity of light. What you have to change is the refractive index, and I wanted, or he wanted actually, to change the velocity as a function of root y. So the refractive index has to be changed by 1 by root y. So it said that suppose if I have different layers where the refractive index is different, and how will it change is that if you go y down, the refractive index change by 1 by root y, then whatever way light will travel from this point to this point, light takes refract due to changes in refractive index medium. And why does that refract? Just to minimize the time, and it would do so it will take something like this, but if I make this change in refractive index very smooth or continuous, then whatever this path will be taken by light will be the same what I should make my slide to get this fastest path. And now what we're gonna do is do the same thing with soap. And now where does soap come in between? So we know that to get this shortest time thing, what was the question? To go from point A to point B, to find what will be the fastest slide. He did it by using light, that I give the light this environment, the velocity change by root y, or the refractive index change by 1 by root y, so the path will be the same. So we see that this problem for going from point A to point B in the fastest way was solved by light. That was his beautiful solution, that he actually merged this thing that you have to travel fastest under gravity and used optics to solve the problem. Somehow here, this gravity and this optics merged together. The light gave you the solution for this problem, which is so beautiful. And today we're gonna do this problem, solve this problem by soap film. So that's another interesting thing, that how nature is so connected. Of course, the solution was so beautiful, and how today we look forward towards all this theory of everything, and we see that how electricity, magnetism are related, how all these things are related. And in this journey of science, where it's all interdisciplinary, nothing is divided by subject, today we're gonna solve the same problem using soap film. So let's see how we're gonna do it, and what will be just something, it looks something very weird, right? That how will soap solve this problem? So let's see. So for that, let me first take you a little bit about why soap is going to do this. Is because of the surface tension property of soap film, which says that it tries to minimize its area. So if we have a soap film, what will it try? It will always try to minimize its surface area. I have this frame So there are 2 pins, and if I merge this in the soap solution, then it gonna make a film between these 2 points. So it has to attach these 2 points, and let's see how will it make the film. It's simple as that, it's a straight line. Why? Because it has to merge this, and there is this depth, and how will it try to do is this a straight line, because that's the shortest way how to connect 2 points. But there is an interesting things come. I have again these 2 points, but what I have done here is this, there is this change in the depth of how it has to travel. So when if it goes just straight, I can see the depth here is more, but depth here is lesser. So when it will travel in this way, for the area will be multiplied by a smaller factor, but here the length covered here will be multiplied by a bigger factor to calculate the area. So what would it try to do is, it will try to sort of go in this path where the depth is lesser more than it would try to do in this one, which is actually the same thing as light do is like when it moves in different mediums. Suppose in one of the medium the speed is faster and in other it is slower. So here it is something like this with slower speed and this is faster speed. Why? Because for light it's that time it take has to be minimized. So what it will do is, it will try to make its path maximum where the speed is faster, but here it will try to maximize its length where the depth is smaller. So it's something similar like more refractive index, which means it makes more difficult for light to move, is same as more depth, which makes the area more, and it like sort of don't want it and prefers lesser depth thing. So let's see how does this look like. So here we see that this soap film bends, and it bends exactly the same way how the light will bend. If here the refractive index was 2 and here it is 1 as the depth ratio, it's same as n1 sin theta 1 is equals to n2 sin theta 2. Also we can get here that it is h1 sin theta 1 is equals to h2 sin theta 2. So what did we actually see is this, that as we wanted to change the refractive index in the ratio, we can do the same thing by changing the height, and what my ray diagram will look from my soap film. So this same analogy when we use that, we wanted to change the refractive index by 1 by root y. So what we can do, rather than now changing this slab stepwise, we will change this height as 1 by root y, as we wanted to change the refractive index. So here we have made so this is the frame we have. So we have to go from point A to point B, and how does this height changes? The height is like, so as you know, this is my depth, the gap between the two acrylic sheets. Here if you will see, the gap between 2 acrylic sheets is not a discrete thing, it's changing by 1 by root y. So if it's changing by 1 by root y, it will and if it has to go from point A to B, it will take the same curve as the light will take. If it has to change, if its refractive index change by 1 by root y. So let's see how that curve looks like. And see, here comes the solution. So to go from point A to point B, the fastest slide, how it should be made, we can see the answer through this soap film. Isn't it interesting that this problem of falling an object under this gravitational force was solved by light and even by soap? This tells us the secret behind nature, how beautifully everything is so connected. And with the help of soap, with which we solve this gravitational problem, we can also solve some of the problems which are even difficult for computers to solve. That's the beauty of the universe, to play with things, to make some stuff and problem solving. Thank you.